Hello everyone. Today we are going to look at neural network architecture. So, in fact, a neural network will look something like this. You have a layer which we call input layer, and then followed by a hidden layer, followed by an output layer. So it's not necessary to have the hidden layer, but usually let's say this is input layer, hidden layer, and this one is output layer. So usually this layer is not counted in terms of when we say L layer network. So this would be one hidden layer plus the output layer will form the depth of the neural network. So in this case it is two layer network. So one hidden and one output layer, and usually you have connections from every neuron to every other neuron from one layer to the next, and so on. And whatever comes output is X. Usually this can also be represented like X1, X2, X3. So this is the terminology for neural network architecture. Let's look at a few of them to gain some clarity. So the first one we can look at it is like very shallow. So shallow is essentially don't have any hidden layer. All you have is like input layer, and then you have an output layer, right? So all of your input is feeding into this layer, and then this is one layer network. Okay, then let's look at a two-layer network. This is actually a two-layer network. We already seen this one. So there is one hidden layer. Usually when we say deep neural network, it has more than 4 or 5 layers. So let's look at some of the. So it could be something like this. We have these are input layers, and then let's say the hidden layer 1, right? So this is hidden layer 1, HL2, let's say hidden layer 3, hidden layer 4, and this is output layer. So this one you can say 4 plus 1, 5 layer network. And again, each of these are connected. Because it's so messy, I'm not going to draw everything, but generally every neuron is connected to every neuron in the next layer, especially in the fully connected neural network layer. Okay. Generally the parameters, so when we say architecture, we are going to say number of hidden layers is one of them, number of output layer is one. Let's list out all the architecture. Hidden layers L, and then let's say in each hidden layer, let's say L1 layer, you have number of units. This is number of units in hidden layer 1, number of units in hidden layer 2, number of units in hidden layer 3, and so on. So that one in L1 layer we have 4 units or 4 perceptrons, L2 3 units, and L3 2 units, and final output layer is 1 unit. So so far we haven't looked at what each perceptron is in this one. So this will have something known as a activation function and an aggregator of weights. We will look in that in the next example. Let's understand basics of neural network using a simple neural network with a logistic regression. But before that, let's understand the data that we can use for this example. Consider a data set x comma y. This y is let's say this x represents 4 variables. Let's say x1 is age, x2 is family history of cholesterol, of let's say heart disease, x3 your cholesterol readings, and let's say and then y is whether or not he needs a prescription, and let's say x4 is weight and prescription for cholesterol, needs a prescription for cholesterol. So this is usually either 0 or 1, and this one are any continuous variables. So our goal is to predict y. So let's say the prediction is we call it y hat. Using we could simply predict using some some linear function with weight w and b. However, linear regression usually has a problem that y cat can be less than 0 or y hat can be greater than 0, greater than 1, or close to infinity, which it doesn't mean in terms of what we are expecting. So often in logistic regression, this output is passed through a logistic function. So y hat is usually it is passed through logistic function with weights w on x plus some bias parameter. So where let's say if this variable is equal to z, you can represent this one as 1 by 1 plus e power minus z. So this function, sigmoid function or logistic function, is actually this one. So why is this important? So what happens is, let's say you have this yours wx plus b, it can go from minus infinity to infinity. So it is applied through a function, and that function is always between 0 and 1. So this is 0, and let's say this is 1. This is sigma of z, and there whereas this one is z. So it is very useful here because the value always lies between 0 and 1. So how is this equal to our simple neural network? So we can actually represent something like remember x2, x3, x4, and it has one output layer. So this is x1, x2, x3, and x4. So all of these are going into this neuron, and it has its weight w1, w2, w3, w4, and this goes through some function. Usually there is a function sigmoid, and then it produces an output y. So this is the reason why we call it and there's another bias term called b. That's why logistic function is equal to a simple neural network where activation function is sigmoid. There are other activation functions which we'll look into detail. Other activation functions such as tanh, ReLU, linear. This is essentially when you're using linear regression, you can use this one where f of x is actually equal to x, right? So tanh values lies between -1 and 1. This is very similar to sigmoid, but instead of 0 to 1 it lies. ReLU is essentially it's a maximum of 0 or z, so it or actually x, the output is never less than 0. So these are most often used activation functions. But let's go back to our logistic regression and see how we compute the weight. So that our goal is to find w comma b such that y hat minus y is minimum for all training examples. So let's say you have a training set like x1 y1 x2 y2, let's say xm ym. So there are m data points and these are training set, and our goal is to make sure that for every data point this is minimal, or in other words the sum of y minus y hat, let's say average over all m examples is minimum. So how do you compute this w and b? One way is actually the best way that is defined in statistics is something known as loss function. So for linear regression, we often use something known as yi minus y whole square for each training example. You could actually simply use y minus y hat, but most often this varies from -1 and 1, so it's not a reliable way. Or you can use absolute value of y hat. There are cases where you can use. In case of logistic regression, the best loss function is actually it's in the form of y log 1 y hat plus 1 minus y log y hat. So this is the loss function. Actually it's there's a negative term. So there are many functions that we could use, but this is the best loss function, and it is convex function. So which you will see why it is useful to have a convex function, and you can easily identify w and b using what is known as gradient descent approach. So again, cost function is, let's say this loss function as L y comma y hat. Cost function is average of m training example loss of y comma y hat. So this one we can represent as w and b. For given w and b, we can compute a cost function. So remember, loss function is for each training example, and this one is whole data set. So let's look at, but where is w and b in this equation? Remember, you have y log y hat is nothing but sigma of wx plus b plus 1 minus y log of, actually this is 1 minus y, 1 minus sigma of wx plus b. So this is or if you can simply expand this one, 1 by 1 plus e power wx plus b plus 1 minus y log, so 1 minus 1 by 1 plus e power wx plus b. Actually it's in fact minus wx plus b minus wx plus b. So our goal is to minimize this across all training examples, and there is our w here and b here. So the way we derive this w and b is to understand how we derive this one, we need to know what is known as gradient descent. So gradient descent. So imagine there is a function w and b. Let's represent that function. If you have two variables, then let's say this is our b and this is our w, and let's say this is our grid loss function or cost function, j count w. So usually as we are going, let's say the w goes in this way. So for some value of w, no, this y goes like this, and remember I'm actually some kind of a curve like this. It's like a ball shape, and somehow, you know, let's say this is where our minimum occurs. So there is a specific value of w, let's say g and b global, where the minimum value occurs. So see, for this particular value of b, you know, let's say it occurs here, and this particular value of w, which is occurring here, we have this function value is minimum. So that's what we are trying to do. And in order to, so for initially when we randomize, we might be starting here. So for certain values of b and certain values of in this function, you know, maybe certain values of w. So when we initialize start, we initialize with some random w and some random b, and then you can compute a j of wb using the formula that we have just seen here. You just substitute w and b, you get some value that is our cost function, and then you can move along this surface and try to identify this w and b. So what gradient descent helps is it derives some concepts from derivatives and try to identify the proper approach to traverse the surface. So this surface is known as is a cost function, and we are traversing in this surface so that we get to minimum in a minimum amount of time, and that is where gradient descent helps. And when we have a convex function, the traverse is easier. We are guaranteed to obtain a minimum. So in other case, when it's not convex function, usually something like this. So the global minima is somewhere here, but you might get stuck here or here. But in order to we may not be able to reach here when it's not convex function. So our goal is, like, at every point in w, we will compute, let's say at a point k minus 1. So we are computing for we are deriving and dw. So this derivative gives the direction in which we have to move, and then similarly bk is bk minus 1 minus alpha, right, dw. So remember, this is known as learning rate, and this is the derivative of our parameters on our cost function. So our goal is to iterate this one. You know, let's say while wk, let's say wk minus 1 is less than epsilon, some small value. So while that values are true, and also bk, so all these are true, we just exploring this loop. So this is how we estimate wk and bk. Let's recall what we just looked at here. We looked at logistic regression. We formulated what is known as a cost function for logistic regression, which is essentially sum of loss function. loss function of y comma y hat, and we were trying to and cost function is it has two parameters, j and w, and we were trying to identify the combination of w and b which minimizes this whole loss, minimizes loss. So the way we did is we defined for this cost function we used a gradient descent and we essentially looped something like, we estimated wk as wk minus 1 minus alpha times dou w by actually dou j by dou w. So we estimated w by iterating few times until the difference between the previous value and minus wk minus 1 is negligible, some epsilon, where this could be like 10 power minus 8 or something like that. Right, so this was what we did in logistic regression, but what does it have to do with the neural network, and how do we do that? This neural networks, remember we have this x1, x2, x3, x4, and you have this hidden layer, and you're getting y hat. So let's expand this part and we'll see what happens in this neuron. So the first thing that happens is let's put like above. So you're just you're multiplying each of these variables, x1, x2, x3, x4, and then you're applying a function, the sigmoid function, which is activation function, sigma of wx plus b, and then you're generating y, and then you're generating loss of y comma y hat. So again you have what goes into here is x1, x2, x3, x4. So it takes this input, so this is what happens in the neural networks. So it's going forward, it's fairly straightforward. So you initialize with some w is equal to some initial values, like let's say w1, w2, w3, w4, and you have a value b. This is, let's say, 0, 0, 0, 0. Initial values are like this, right? You have these different values. So initial values are fairly straightforward compute. You can multiply w times these initial values and then add b. So this is going forward, this we can compute easily, and then you just apply sigmoid function, which is 1 by 1 minus e power minus z. Whatever value you get here, you just substitute in this one, and then you get y hat. And then you already know your example, so let's say for this example you know y hat, so you can compute this loss of y comma y hat, which is remember as y log y hat minus plus 1 minus y log of 1 minus y hat. So it's fairly straightforward to compute this one once you know. So this going from these input variables to applying weights and then computing activation function and then computing loss function, this is forward pass. So you're going to do this for each example, whereas the weights are updated when going back. So you can compute derivative of activation function by and then derivative of w with respect to this function. So that gives you weight comma w. So we are getting this new weights when we are going back. We are estimating these. in order to understand these concepts of back propagation, so this going back, we are updating weights. In order to understand this, we need to understand some concepts of derivation, but we are not going to go in detail. But you can imagine that back propagation involves computing derivatives, and then those derivatives will result into new, so those derivatives can be used to update your weights as well as your this bias parameter. So in the back propagation, you're updating weights. In the forward propagation, you're just applying weights and getting the loss function. So you do this iteratively until your this whole sum of this cost function is minimum.